All right, let's jump right into this explainer and uncover a single, kind of spooky rule that underpins absolutely all of physics. And I literally mean everything. We are talking classical mechanics and electromagnetism, all the way down to quantum theory and general relativity. It's this incredible mathematical detective story that spans centuries, and it all boils down to one surprisingly simple optimization principle. To really wrap our heads around this universal rule, we're going to rewind to the 17th century with a classic historical puzzle. It's known as the problem of fastest descent. Basically, if you want to slide a mass from point A to point B, what shape of ramp gets it there the fastest? Now, common sense might tell you it's a straight line, right? The shortest distance. But if you bend the ramp down at the beginning, the mass actually accelerates to a higher speed earlier, and it ends up beating the straight ramp. Even the great Galileo took a swing at this and incorrectly guessed the answer was the arc of a circle. Fast forward nearly 60 years to 1696. The brilliant, albeit pretty arrogant, mathematician Johann Bernoulli threw down the gauntlet and posed this exact puzzle to the world, giving everyone 6 months to solve it. Well, when nobody did, he extended the deadline, pretty much specifically to goad a retired, grumpy Isaac Newton. Newton was working at the Royal Mint at the time and got this challenge in the mail. Highly irritated, he grumbled that he did not love to be dunned and teased by foreigners about mathematical things, but the problem was just too enticing. Out of sheer irritation, he stayed up all night, completely solved it by 4 a.m., and then just submitted his answer anonymously. Bernoulli took one look at that anonymous solution and supposedly said, "I recognize the lion by his claw." But here's the real twist for us. While Newton's brute force calculus was undeniably brilliant, Bernoulli's own solution was a stroke of absolute creative genius. Bernoulli basically hacked the physics problem by stepping entirely outside of mechanics. He realized that to find this curve of fastest descent, which literally means shortest time in Greek, or the Brachistochrone, he could treat that physical mass exactly like a ray of light. See, Bernoulli actually pulled his inspiration from ancient optical physics. Way back in the 1st century, Hero of Alexandria figured out that light bouncing off a mirror takes the shortest physical distance. But centuries later, Pierre Fermat realized that when light passes from air into water, it bends, it refracts. Fermat brilliantly deduced that light isn't taking the shortest distance. It's actually optimizing for the shortest time. And this is where things get really cool, because it beautifully illustrates how nature just loves optimization. Take Snell's law, for example. It turns out this famous law of refraction isn't just some random rule. It naturally pops right out of the math when you simply demand that light travels in the most time-efficient way possible between two mediums where it has different speeds. Section 1, Mechanics meets Optics. Modeling a falling object as a ray of light. To do this, Bernoulli imagined the space as a series of infinitely thin layers. Because energy is always conserved, the mass's velocity increases proportionally with the square root of the distance it drops. It's exactly like light entering thinner mediums where its speed increases. So he plugged this velocity into Snell's law across every single infinitely thin layer, creating this continuous mathematical chain. He literally forced the mechanical falling object to obey Fermat's optical principle of least time. The real kicker here is that when you map this optimal optical path onto a physical ramp, the equation you get is for a cycloid. That's the path traced out by a point on the rim of a rolling wheel. The absolute fastest possible shape isn't a straight line, and it definitely isn't Galileo's circle. It's a cycloid. Bernoulli had essentially proven that mechanics and optics, two entirely different fields of physics, shared the exact same fundamental character. Section 2, the discovery of action, moving beyond time. So a student of Bernoulli's, Pierre-Louis de Maupertuis, started wondering, does nature have an even deeper expense account it's trying to manage? He proposed a brand new concept called action, which he defined simply as mass times velocity times distance. He argued that whether you're a ray of light bending through water or a ball bouncing off a brick wall, nature always manages this specific mathematical expense to make it as absolutely small as possible. It's like the universe is incredibly lazy, but in the most mathematically precise way imaginable. Now, you'd think people would celebrate this massive, groundbreaking idea, right? Nope. Maupertuis was absolutely roasted. He'd kind of picked this idea out of thin air and didn't have the rigorous math to back it up yet. His former friend, the famous philosopher Voltaire, completely turned on him. He accused him of plagiarism, called his physics terrible, and basically just called him stupid. In fact, Voltaire wrote an entire 32-page pamphlet solely to destroy Maupertuis' reputation. But you know, the story doesn't end there. Enter Leonard Euler and Joseph-Louis Lagrange, two of the greatest mathematicians in history. They took a look at Maupertuis's highly ridiculed idea and realized he was actually right. Over the next 2 decades, Euler developed a clunky but functioning new branch of calculus to calculate this infinite optimization. And then a 19-year-old self-taught genius named Lagrange eventually came along and provided the general mathematical proof. Section 3. Unifying the universe. The modern form. Lagrange, and later a physicist named William Rowan Hamilton, took this somewhat clunky theory and turned it into an absolute physics machine. To find the path of least action out of an infinite number of possible paths, Euler converted Maupertuis's formula into an integral over time rather than distance. And crucially, he anchored it to the fact that the total energy of the system, that's kinetic plus potential energy, must remain completely conserved across the entire journey. When all the calculus dust finally settled, it left us with arguably one of the most important equations in all of physics, the Lagrangian, denoted by L. It is a beautifully stark formula representing the kinetic energy of a system, T, minus its potential energy, V. There are no forces, no messy directions, just the system's kinetic energy minus its potential energy. Which leads us right into Hamilton's principle. Mathematically, it tells us that if you take that Lagrangian, remember T minus V, and integrate it over time, the variation between the true path an object takes and any other imaginary path will always be exactly 0. Out of literally infinite possibilities, nature always perfectly threads the needle to ensure the specific integral equation zeroes out. Now, I know what you might be thinking. Why do we need all this highly abstract calculus when we've already got Newton's trusty F equals ma? Well, Newtonian mechanics relies heavily on forces and vectors. That means you have to perfectly calculate every single angle, direction, and push. Lagrangian mechanics skips all those messy directional vectors entirely. It only relies on energies, which are just simple, easy-to-use scalar numbers. And that right there is the true superpower of this discovery. The Lagrangian acts like this automatic math machine. Imagine trying to calculate the wild swinging of a double pendulum using Newton's vector forces. It is an absolute nightmare. But with this, you just plug your basic kinetic and potential energy into the Lagrangian, and the correct equations of motion for incredibly complex, chaotic systems just naturally pop right out. Just a quick caveat for the physics purists out there. Scientists technically call this the principle of stationary action today. Just like finding the flat bottom of a curve in calculus by setting the derivative to 0, you're finding a stationary point. The action isn't always the absolute minimum possible, but it is always stationary, meaning tiny deviations to the path result in 0 change to the action. So, what's the big takeaway here? Why does this 300-year-old mathematical detective story even matter to us today? Well, because this isn't just a neat trick for sliding blocks on ramps or swinging pendulums. This single optimization rule successfully unified completely disparate fields of science. The exact same mathematical principle that dictates how light bends through a glass of water dictates how planets orbit around stars. And even more wild, at the turn of the 20th century, this exact principle of action was the key to solving the UV catastrophe, providing the initial spark that literally birthed quantum theory. What started out as a heavily ridiculed guess by Maupertuis, a guy who basically just had a hunch that nature had a true expense it was managing, compounded over centuries. Through the minds of Bernoulli, Euler, Lagrange, and Hamilton, they proved his intuition right, cementing it as the foundational mathematical truth of our physical reality. Which leaves us with a pretty profound realization. We started by treating a falling mass like a ray of light, and discovered an optimization rule that controls the entire cosmos. If a single equation governs the trajectory of colliding stars, invisible quantum particles, and perhaps even the complex behavior of life itself, what other hidden, spooky optimizations is nature quietly running right in front of our eyes, just waiting to be discovered?